Hi everyone, sorry I couldn't be there today. I'm going to run through this video, but there are going to be times where you are expected to pause so that you can then look at the answers after you try some things yourself. Okay, so we're going to be using these rational functions and identifying one more aspect to how they're going to look on the graph and how to simplify them, because we can simplify anytime you have a rational number, and we're going to apply that to rational functions. So starting with this table here, when we look at 24 divided by 30, we know that we can divide both of those by 6 because those are factors that go into both of them. The 2 and the 3 makes the 6. That creates the 24. The 2 and the 3 creates the 6 for the 30. And so we can actually divide out those evenly because the 6 and the 6 creates a 1 when you do 6 divided by 6. So we're going to get rid of a 2 and a 3 in both the numerator and denominator, and it would be left with 4 over 5. And so the same idea holds for when we talk about polynomials. When we look at a polynomial, we can try and break it up into the factors. And so just like we talked about last unit, we can break these polynomials up into the factors by factoring. So the top polynomial could be broken up into x minus 3 and x plus 2. And this is why it's important for you to remember how to factor so you can simplify these. And then this is going to make the x plus 2 show up in both the numerator and denominator because it is both a factor of x squared minus x minus 6 and x squared minus 4. So if it's a factor of both, we get to divide it out because it's just a factor of 1. And it's going to leave us with just an x minus 3 over an x minus 2. The same idea holds for c. If I factor both the numerator and the denominator, I can see if they share a factor. And I can see here that they share the factor of x plus 3. So if I divide out x plus 3 and x plus 3, that's just a factor of 1. And so it leaves me with x plus 5 divided by x plus 6. Now, a lot of people struggle with the idea of when can I cross things out? And so an example like this is in number 3. Are these the same thing? X divided by x squared minus 1 and x divided by x minus 1. I have a lot of students think that, oh, I see an x here and I see a square here, so I can just cancel those out so that they're the same. But is that actually true? Are they the same factors? So if I factor out the x squared minus 1 into our difference of squares, x plus 1, x minus 1, do I have any of the same factors in both the numerator and denominator that I can cancel out as a factor of 1? And no, the x cannot cancel out the x plus 1, the x cannot divide out the x minus 1. So these are not the same, so you cannot do this. The only time you can divide things out is when they're the exact same thing with multiplication, okay? So we are going to practice that, trying to simplify our rational functions by using factoring. And we're also going to try and see what numbers would be excluded from that domain. So the domain is going to be where those asymptotes are and where a new thing is going to appear soon. So if I factor number 4 by GCF, I take out a 3 and I'm left with x minus 3. And in the denominator, I can factor this into x minus 3 times x minus 3. So right away, I know that the domain exclusion is going to create a vertical asymptote at x equals 3. So everything is going to be true from negative infinity to positive infinity except the number 3. So for this exclusion, I'm just going to write that x cannot be 3 because of that denominator. And so that always comes from this right here. So after I factor it out, I want to figure out what can be divided out to create my new function. So that leaves me with 3 divided by x minus 3 as my simplified rational function. Okay, so this is where one of those examples is that I want you to take a pause so that you can do the rest of the examples in this box, so all the way up to number 9. So take a pause right now. Welcome back. I hope you were able to get these questions done. So I'm just going to show you the answers right here. Please make sure that you do your domain exclusions before you start dividing things out, because it does still affect your domain even if you divide it out. It still appears as a number that cannot be in the denominator, otherwise you would get an undefined value in the denominator because you would get a 0. For instance, in number 8, if I put a 2 in to the original function, my denominator would end up being 0, which is not possible. You can't have a denominator of 0 or else that's undefined. Okay? So we are going to take that idea and apply it to a new function. This function, x squared minus x minus 6, all divided by x minus 4. So we want to predict the vertical and horizontal or end behavior asymptotes and then find our intercepts. Okay, so for this, remember our end behavior asymptote, I'm just going to make an EBA, is our numerator degree is equal to our denominator degree. So we have to divide our coefficients. So since we have an x squared and an x squared, that's a 1 divided by 1. Thus, our end behavior asymptote is supposed to be y equals 0. Okay? All right. If I factor this, I can help find those vertical asymptotes. So x minus 3, x plus 2, divided by x minus 2, x plus 2. So because of that denominator, I think I'm going to have an asymptote at x equals 2 and x equals negative 2. Then my intercepts, my y-intercept, I just substitute in 0. And it's actually better if you substitute 0 into what the function's going to be after you divide it out. So because I can divide out that x plus 2 on the left-hand side, this leaves me with x minus 3 over x minus 2. So this is where I'm going to use to find my intercepts. So I think what's going to happen is that the y-intercept, if I plug in 0 for the x here, it's going to be 0 minus 3, 0 minus 2, thus positive 3/2. The x-intercept, remember it's just the numerator set equal to 0. Because if you were to multiply the denominator by 0 on the other side, it would just make a 0. So my x-intercept is going to be 3. So 3, 0 for my x-intercept, and 0, 3/2 for my y-intercept. Okay. So based off that prediction, let's actually see what it looks like on Desmos. So right away, I think I have an end behavior asymptote at y equals 0, 2 asymptotes, x equals 2, x equals negative 2, and some x and y intercepts. So you can pull out Desmos yourself, or I'm going to show you what it looks like right here. So right away, I hope you can kind of see, even though there's not dotted lines, I hope you see that there's actually something wrong with what we just predicted. So we do have that y equals 1 asymptote. It does glide along that y equals 1, if you can see from here to here. It does have the asymptote at x equals 2 going up and down. But there's no there's no asymptote at x equals negative 2. It really looks like it kind of goes through. So what happens there? So what happened there is because when we divided out the x plus 2's, okay, that actually created something called our hole. So I'm going to rewrite this down here. So when we factored it out, we found that there was a matching factor in both the numerator and denominator. We can divide it out. So it still was in the original function. It still should be part of your graph. But if it divides out, it doesn't create an asymptote anymore. What happens is that this x minus 2, it creates our asymptote. But this right here, our x equals negative 2, actually creates a hole. So a hole is literally going to be an open circle at that spot. And it might not appear on Desmos itself, but it does appear, and when you graph it, you're going to draw an open circle. And so the hole is going to be a physical point on the graph. And so it's going to be at the x value of negative 2, because I crossed off the x plus 2, thus I have negative 2. And then to find out where it lies on the y, you have to substitute it into the simplified function. So x minus 3 is now going to be negative 2 minus 3. and x minus 2 is negative 2 minus 2. So I have a negative 5 over negative 4, which makes this technically 1.25 positive. So I'm going to have an open circle hole on my graph at that exact point. Okay, so I want you to use everything that we talked about to fill in this table below based off the holes in the end behavior asymptote. The only other thing I'm going to tell you is up here I figured out my end behavior asymptote from the x squared and the x squared. But what you really should do is actually wait until you simplify it and figure out here. So the degrees are still the same. Most of the time it won't have an effect. I'll still have like a 1x divided by 1x, so it's still an end behavior asymptote of y equals 1. But sometimes, very few, but sometimes it actually will change depending on what you simplify out and divide out. Okay, so I want you to try these 6 questions below based off of everything we've talked about. Pause this video and come back when you are ready to check your answers. Okay, so here are your answers. Hopefully you were able to see what your end behaviors are and your vertical asymptotes are from what we've talked about before. The holes is the only thing that's new. So the hole just gets created anytime you divide something out. It doesn't always happen. And then once you find the x value that you divide out, you substitute it back in to the simplified function to find out what the y value is at the hole. And what I was talking about before is figuring out the end behavior asymptote after you simplify it is like a number 16. There actually is no end behavior asymptote, even though in the x squared and the x, because the original had the numerator greater than the denominator, you would have a slant. But after you actually simplified out the x plus 6's, that leaves you with just x minus 1, which is just a linear function itself. So if it's a linear function all by itself, you can't have a linear asymptote because it just creates a line by itself. And you would just have a hole on that line at negative 6, negative 10. Okay? All right, so now we are going to put everything together on a graph, and then you're going to do some practice questions yourself. Okay, so we're going to put this all together. So from this function, the thing that matters the most from the original function, the very first thing you should do is the domain. So right away, I know that there's going to be a spot at 0, and there's going to be a stop at 2. So when I do my domain, I know it's going to go from negative infinity to 0. I'm going to take a stop or a break, go from 0 to 2, take another stop, and from 2 to infinity. After you fill out this information, this is when you can work through what you can divide out. So since I can divide out the x minus 2, it's going to leave me with, please don't make the numerator go away. Please put a 1 as a placeholder, and then it leaves me with 1 over x. So now I'm going to work with 1 over x when I create my graph. But when I crossed off that x minus 2, that does mean I'm going to have a hole at x equals 2. Okay. So for end behavior asymptote, now that I have technically my numerator is less than my denominator, I have y equals 0. My vertical asymptote, I have an x in the denominator, so I have x equals 0. My hole comes from if I substitute in 2 to the simplified version, so 1 over x equals 1 over 2. My x-intercept, if you notice, my y equals 0, my x equals 0, I shouldn't have any intercepts because both of my axes are asymptotes, so that shouldn't touch. You should also just find out that when you substitute it into 1 over x for the y-intercept, you get 1 over 0, which doesn't work. And also when you set the numerator equal to 0, that doesn't work. So that's how you find your intercepts. And so now we just have to put this all on our graph. So we have y equals 0, we have x equals 0, and our hole at 2 and 1/2 is literally going to go 2 and up a half, and you're going to put an open circle there. And that's going to represent your hole. Now, you have to make it very obvious that it's a hole. You shouldn't just put a tiny dot. Make it very obvious so when I grade, I can see that you know your hole. And then you just find your pattern like you always do. So you can find your pattern, or you can plug in points. Okay, sometimes you might struggle to graph it if there's something in the numerator itself. So just always remember, you can plug in points into the equation to find the rest. Okay, so now that I've done this example, I want you to pause the video and work through the rest of this note packet and come back to check your answers. All right. Okay, so here are your answers. Hopefully number 18. You saw there will be a break at -3 and 3, but one of them is going to be a vertical asymptote and one will be a hole. You won't have any x-intercepts because of that asymptote at y = 0. Here's 19 and 20. 19 is hopefully pretty straightforward. The only thing that you should be careful of is that the y-intercept, if you calculated it, actually ended up being the hole. So you won't have any because it's going to be a hole. And then in number 20, you might have struggled to graph it because you're left with that x in the numerator, and typically we haven't seen an x in the numerator before. So once you graph your asymptotes, your y-intercept, and your hole, you can plug in other points, like I did down here at I knew that there was going to be another point at -6. So I just substituted in -6 into the equation to find out that I should have a point at -6 too. You could plug in -5, you could plug in -3.5, you can substitute anything in, but you could also just follow the pattern that because the y-intercept was technically 3 to the right, it was technically 3 to the right and 1 down, you would do the opposite and go 3 to the left and 1 up. Same thing with the hole. Even though it doesn't exist on the line, it does exist on the other side. So if you go 1 to the right, you would go 1 down. Because if you substituted in -4, it should match. So -4 divided by -4 plus 3, -4 over -1, so that equals 4. So you know you'll have a point at -4, 4. So when all else fails, just plug in points to find other spots on your graph. Okay, hopefully this wasn't too bad. You'll have your homework, and then we will do a summary all together when I see you on Friday. All right, thanks everyone.